Okay, thank you very much. So to get started with the resource theory of tensor networks, I was thinking I give you a very brief introduction to tensor networks and some background and motivation. I guess you know all of this, but yeah, I think it's a bit a particular way of looking at tensor networks, so it's good to kind of see it again. How is this working? Okay. So what kind of problems do we want to study when we use tensor networks? So maybe we want to study quantum many-body systems. Maybe we want to simulate some sort of quantum circuits under some assumptions, whatever. And as we all know, there's a problem with that. And the problem is that like the state space is too big. It's exponentially big in the number of particles or in the number of qubits there. And because of that, it's kind of hard to keep track of everything. But as we also all know, usually states that we are interested in, they have some additional structure. So there's a little bit more structure that maybe helps us to reduce this number of parameters. And one example could be that, if you want to simulate a quantum circuit and you only have, say, 1 and 2 qubit gates, and you have polynomially in the number of qubits, then, describing the list of gates only takes polynomially many parameters. So it's not too unbelievable that there might be a smart description of the state in the end with less parameters. And the way to do it, I mean, what I told you right now is not really like helping anything because, just knowing the gates doesn't really give you any information about what's going on. But the way to do it is to be kind of inspired by many-body physics, where people very strongly believe in some sort of area law for the states of interest. And area law essentially means that you have, how is this? Yes. Essentially means that you have some sort of local entanglement properties, some local correlations in the system. And this is actually the starting point to start talking about tensor networks, which then helps you to reduce the number of parameters. Okay, so how does this work? So I said that, I didn't say it, but it was written there. So tensor networks kind of work well when you have local correlations with respect to some graph. So the ansatz is that you start with a graph, for example, this lattice here, and then you construct a quantum state, and you construct a quantum state by putting EPR pairs on the edges of the graph. So you get some sort of quantum state, and and this D is called the bond dimension, and then you can construct quantum states by applying linear maps locally at the vertices. And in the picture, it would look like this, and then I will always do it like this, that you have these kind of circles, which are linear maps at the vertices. And then you get out a state out of this, and this is a tensor network state with respect to the graph and with respect to the bond dimension D. Great. And a lot of you maybe think of tensor networks in a different way, namely by contracting tensors across some sort of, graph. But this is equivalent to this definition. And I will also later always say, or often say, projected entangled pair state, so PEPs, but it's exactly the same. Great. So I kind of vaguely said why it might be a good idea to think about tensor networks, but in fact, it turns out they're really useful. So many physical systems can be well described by PEPs, for example. And in general, they are very good for simulating quantum circuits. There was, I think, 1 or 2 talks about tensor network decoders, and they're also used outside of quantum, for example, in machine learning. And the thing I want to stress here is that these algorithms that exist, that you can use, they are highly optimized, but they don't scale very well with the bond dimension. So it's still very interesting to find PEPs representations which have lower bond dimension than the known ones. And the star of today is actually not a tensor network, but it's what we call entanglement structures. And when you were listening the last 5 minutes, then I think you know where this is going from these pictures. So, as I told you, tensor networks work like this. You have a graph, you put entangled pairs on the edges, you apply linear maps at the vertices. So boom and boom. And entanglement structures are a very natural generalization of this. So you take, instead of a graph, you take a hypergraph. And when you have an edge with n vertices, then you can put a n-party quantum state on it. And then again, you apply linear maps at the vertices. So examples could be this. So it's like some very regular lattice with 4-party quantum states on it, or this Kagome lattice, which we will also see later in more detail. And then, as I said, you apply these local linear maps, and you see what you can get out of there. Yes. Now, you could ask, why are we doing this? Because it turns out that if the bond dimension is large enough, and if the graph is connected, you can get any quantum state you want out of this. So if the bond dimension is large enough, tensor networks can describe anything you want. So you might ask, why are we even caring about entanglement structures? Well, one reason could be, this is examples for states you can put there, blah, blah, blah. But one reason could be that, maybe you're thinking about some Hamiltonian which has 3-body interactions, and maybe it's much better like modeled by this Kagome lattice, where you put these 3-body quantum states on it. And maybe this can give you better numerics, or maybe it's just a very good intermediate step to find tensor network representations, like PEPS representations. And we will also see an example of this later, so this is something that really works. And one key difference between tensor networks and entanglement structures is that in this kind of simplified setup that I said, where all bond dimensions are the same, it's very easy to understand the tensor network as a resource, because the bigger the bond dimension, the more expressive your tensor network. And for entanglement structures, this is very unclear how this works. And we don't have this notion of bond dimension, and we don't really know what's going on. And this is kind of the key question of the talk. Like, how should we think about this bond dimension for entanglement structures? And to get started, I want to tell you the most natural way to kind of also make a resource theory on these entanglement structures. So if you have some hypergraph that you fix in the beginning and you have quantum states that fit on it, then you say that the entanglement structure built from the one quantum state is stronger than the entanglement structure built from the other quantum state if you can apply local linear maps at the vertices and get the other entanglement structure out. And this makes sense. This makes sense because if this holds, if and only if this holds, then any quantum state you can get out of this psi entanglement structure, the red one, you can also get out of the phi one. So this is really saying like the green entanglement structure is strictly stronger than the red entanglement structure. And the next section of this talk will be there to kind of convince you that this is much more tricky than just this one bond dimension, which makes everything more expressive or less expressive. And to convince you of this, we have to make a detour. So we will go to algebraic complexity theory, and I will tell you a little bit about complexity of matrix multiplication. So what's going on there? To talk about it, it's nice to fix some definitions. So this is something we actually saw before. So it's always called restriction in algebraic complexity theory. So if you have two quantum states and you can do what I just showed you, namely you kind of apply local maps at the single systems, then we say that phi restricts to psi. And we also write this as phi is greater or equal than psi. And many of you know it as SLOCC operations. Great, yes, and similar to tensor network versus entanglement structure, it's of course very easy to understand this kind of notion for two-party quantum states because we have a restriction if and only if we have more Schmidt rank for phi than of psi. And for states with at least 3 parties, it's much more involved. And one very simple reason why this is more involved is that, for example, you can easily construct 2 quantum states that, there's no restriction from one to the other and from the other to the one. But there's also more like interesting phenomena going on. For example, if you take this GHZ state and the W state, you can show that the GHZ does not restrict to W, but you can approximate W arbitrarily well by restrictions of GHZ. And this is called a degeneration. So you kind of lose low-I semi-continuity here. So why is this called algebraic complexity theory? So one question you could ask is, for a fixed D, what's the minimal R, such that the GHZ state that goes up to R kind of restricts to this tensor network on three parties with a bond dimension D. And it turns out that this question is equivalent to the question of how many multiplications R do I need to perform in order to multiply 2 D times D matrices. And naively, you need D cubed for your usual algorithm, but then in 1969, as a lot of people here know, I think, somebody came around and showed that to multiply 2 by 2 matrices, you need 7 multiplications. And, this kind of makes its exponent smaller. So this goes to log 2 of 7, which is approximately 2.81. And this kind of, opened a wide field of research. And this is from Wikipedia, but there has been a lot of improvements on this exponent of matrix multiplication. Now we are at 2.37 something. And in all of this, there's a lot of constructions to kind of find new algorithms for matrix multiplication. And there's also a lot of effort, without much success, to find obstructions for these restrictions. Okay, so, and not only for matrix multiplication, but they also, of course, started then studying just like in general, how can we find an obstruction for, you know, the restriction between quantum states. And this is kind of like the key slide, and after that there will be another chapter which is kind of convincing you of this key slide. But the key message is that we really think that we can use these methods both for constructions and for obstructions to find something out about entanglement structures, and by that to find something out about tensor networks. So for example, you can use constructions for the restrictions of quantum state to find non-trivial conversions between entanglement structures, which might give you better algorithms or whatever. Or you can use these techniques to show lower bounds on the exponent of matrix multiplication to find obstructions for the conversion of entanglement structures. Okay? We do this, and we actually use this Bini-Kabovani-Romani result here to find a non-trivial restriction between entanglement structure. But to convince you of this idea and to kind of convince you that this makes sense and this is powerful, I want to show you an example of this one. So I want to show you an example where we can actually show that there's no conversion between entanglement structures, and we actually use techniques from this algebraic complexity theory. Okay, and for that we will go to Pep's representations of the resonating valence bond state and the substitution method. Yeah, perhaps I should start by telling you what the resonating valence bond state is, which is not so important because I will not go into the details of, you know, anything. So it's just some state. It was studied a lot. It turns out to be important for superconductivity, and it can be constructed as this dimer state up there. And people were so interested in it that they went and they found a bond dimension 3 representation, Pep's representation, and they kind of wrote it in a little different way, but they used the following recipe, which is very much entanglement structure. So what they did is they took this kind of lambda quantum state. Also here it's not so important what this exactly is, but if you put this lambda on a Kagome lattice, then this restricts to the resonating valence bond state. And then they went and then they showed that there's actually a restriction between the 3x3 matrix multiplication quantum state and the lambda. And then because of transitivity, you can just put it on every plaquette of this Kagome lattice, and then you get a Pep's of bond dimension 3 representation of your resonating valence bond state. So far so good. Then a couple of years later, some other people came and showed that actually on the single plaquette, you cannot come from this 2x2 matrix multiplication and restrict to lambda. So on the single plaquette, this is impossible. But they also show that on the single plaquette, you actually have this approximate version. So this degeneration. So you can approximate lambda arbitrarily well with restrictions of the 2x2 matrix multiplication quantum state. And then they do some very smart trick. And then they show that actually using this, it's enough to study a linear and system size number of Pep's with bond dimension 2 to get out your resonating valence bond state. So this is not important how this works. What is important is that this is a drastic reduction in parameters and, you know, opens the door for much more numerics. But I think what is very clear if you look at this is the key question, or maybe not the key question, but a very obvious question is they only show that the 2x2 matrix multiplication cannot go to lambda on the single plaquette, but there's no reason whatsoever to believe why this shouldn't happen on the whole Kagome lattice. Okay? So this would be, again, a drastic reduction in number of parameters to describe the resonating valence bond state. And yeah, and we actually show that this is impossible. And we show this is impossible using methods from algebraic complexity theory. And, you know, as the last thing, I want to kind of walk you through the ideas of the proof. So how you do this is you just assume there would be a Pep's of bond dimension 2, which restricts to the lambda on the Kagome lattice. And then you kind of group together parties. And if you think a little bit about this grouping together kind of gives one of the sides more EPR pairs. So instead of 2, 2, 2, you have 2, 2, 8, and the lambda also gets supported by this EPR pair 3. Yeah, and then this is where you can use techniques from algebraic complexity theory. And this is a very subtle situation because you have a degeneration. So you have to kind of, you know, I mean, it's true that you can approximate the right side arbitrarily well with restrictions of the left side, but we can actually show using something called the substitution method that there's no restriction. And yeah, and this finishes the proof. So I kind of saved you from all the technical parts, but this is the proof idea. And like this, we can find out that, you know, this way of finding a PEPS of bond dimension 2 of the resonating valence bond state will not work. Okay, and that's, I think, already it. So to summarize, what I told you is I kind of told you about this concept which we call entanglement structures and how to see them as resources. And then I told you a little bit about algebraic complexity theory and the complexity of matrix multiplication. And then I kind of advertised this concept that methods from algebraic complexity theory, they can be very useful for entanglement structures and to understand them, both for constructions, so we have some constructions, which I didn't show you, but they are there, and also to find obstructions. And even for this very like practical example, where we can show that this method will not lead to a PEPS of bond dimension 2 of the resonating valence bond state. And because I really wanted to stress these results, there are some other results. So for example, there's some notion of algebraic complexity theory. Like there's complexity classes called VP and VNP, and we show that tensor network construction is VNP. And we also calculate some tensor ranks of entanglement structures. Yes, and that's some open question is that, you know, there's all these algorithms for calculating, for like multiplying matrices quicker than usual. And, you know, you could ask if this maybe can translate to contracting tensor networks quicker. And one question I'm really interested in is the second one, namely all constructions and all obstructions we have, they don't depend on the size of this lattice. And it would be very interesting to see if you can construct something which only works from a different size on, or if this never works. And also there has been quite some study about canonical forms of tensor networks. And I'm kind of wondering if there's canonical entanglement structures for certain classes of states. So maybe entanglement structures can also be useful there. And yeah, I think that's kind of it. Thank you very much.
Hey, thank you, Vincent. We've got quite a bit of time for questions. So see if you could, come up to the microphone.
Yeah, Vincent, I'm just curious, why do you use this 1979 matrix multiplication algorithm? Do the more recent ones just get very difficult to make use of? Or what about the structure of that one is useful for you?
The 1979 construct. So at some point, the constructions, I think they become very much non-explicit. So it's kind of more results showing that there exists an algorithm, but they don't show what is the algorithm. And the 1979 result, they really have like this intermediate, it's called the Beanie tensor. And then, yeah, and with that, you can kind of still work, whereas with the other ones, you can not really work.
Yeah, great. Thank you.
Hi, thanks for the nice talk. So I wonder, because we know that for tensor network renormalization group, we have this kind of unwanted local correlation, which we want to get rid of. But in your picture, you use this kind of local entanglement map, which you claim that it will be more efficient as a tensor network representation. So I wonder whether in your application, this can be only used to study like the local phenomena, like a physical system with just like a short range correlation, etc. Can you comment about that?
I'm not sure I understand the question.
Okay, sorry, but maybe let me rephrase. I think that, for example, if we use the tensor network renormalization group, we also have this kind of ring structure, but this will capture only the local correlation. But in the end of the day, we want a long range physics. Mm-hmm. Right, but in your picture, you use this kind of entanglement graph, and by mapping, you can also construct some tensor network representation. But I wonder whether in this kind of adoption, you can only study the low-range physics or not.
I think not, but I think we never thought about this. But I think by using appropriate appropriate many-body states on your entanglement structure, you can also like what you're saying for the tensor networks is that you have to make the bond dimension bigger, and then you get also long range.
Yes, I mean that if you have this kind of short range correlation, this will just cause a higher bond dimension, but you got nothing because you just spend a lot of the information storage for the local physics. But we want a long range physics. Mm-hmm. Yeah, that's like a typical issue in the tensor network renormalization group, I believe. So
yeah, I think we also have this issue.
Ah, okay.
Yes, I think it's very. I mean, it's very similar to that. Yes.
I see.
Yes, I think it's only for the small correlation length. We try to make it a little bit smarter. I think. Yes.
I see. Okay. That's what I'm thinking. Okay. Thank you.
Hi, I was just going to ask you to explain again how you use that matrix multiplication result in your work, because that was like the interesting part for me, but I didn't follow. So how was that theorem? Like, how is the fact that you can multiply matrices in like 2.8 n to the 2.8? Like, how was that used?
No, this one is not explicitly used. What is used is it's like one of the follow-up results by Bini, Capovani, and Romani, and I don't know. They have like, okay, I don't know, it doesn't really matter, but they have, here. So they have some sort of smart construction on a single plaquette to, I think, multiply 2 by 2 matrices, except for one of the entries. Like when you think of multiplying 2 by 2 matrices, but you kind of ignore the lower right entry, then they can do it approximately with 5 multiplications, I think. And for that, they have kind of a smart way of finding a degeneration, so this approximate version of restriction between the GHZ5 and it's called the Bini tensor, and we kind of extend this on the lattice and kind of use it on the lattice to I think we get out of like GHZ5 states on the lattice, we get out these Binis on the lattice.
I see. So the idea is that you use a similar like proof technique from that. Like that's how you used it.
Yeah, very much. But it's I mean, you have to stress that it's different than just putting it plaquette by plaquette on the lattice. So there's a bit more to that. Yeah.
Okay. Thank you so much.
Hi. I have a bit of a tangential question. Have you heard of this DeepMind paper about like using reinforcement learning to like find faster matrix multiplications?
Yeah.
So I was wondering if you could comment like if there is any applications of that work in finding like entanglement structures, or I mean, I really don't see it, but I wanted to know your opinion.
So all I know is, I mean, I didn't read it. I don't really know what they are doing, but what I know is that it's kind of like ignored in this community. So I would guess no. Like they didn't really like jump onto the they didn't really care about it, I think. So I don't know. But I didn't try. Yeah.
So thanks for the talk. As far as I understood, you always, like in this entanglement structures, you always consider like the same kind of state for each of the things, right? I mean, but can you mix this? Say like you take triangles and like one of them is GHZ and the other one is W, and then
yeah, that's a very good question. Yeah, of course, and it gets more complicated. I think I did this mainly for the because it's a 20 minutes talk. I wanted to like reduce complexity, and actually on that occasion you can also say that like I said that for tensor networks the bond dimension kind of says how expressive it is, but once you allow different bond dimensions it's not easy anymore. So yeah, also yeah.
Is there something that you can do like with a mixture that you can't do with like always the same thing? Like do you have an example like that, or?
So there's this quantity called the quantum max cut. No, quantum max flow, quantum min cut, quantum max flow. Yeah, it's not the max cut. And actually there's on a very small tensor network where you can choose all bond dimensions differently. There's some very non-trivial conversions between different tensor networks. So already on the tensor network level, this is possible. Yeah.
Thanks.
Are there any more questions? If not, then let's thank the speaker again and to the next session.